for the lecture on complex analysis. In previous lectures, we discussed about the complex integration and series expansion. Here in this lecture, I would like to discuss only on series, that is Taylor series, as well as Lorentz series expansion related definition, as well as some exercises related to series expansion. Power series expansion. You know that in that power series, a series of the form summation n running from 0 to infinity an into z power n, or summation from n 0 to infinity an into z minus z naught to the power of n is called a power series, where z is a complex variable and an is the called the complex constant. Here we start with the Taylor's theorem. If f of z is an analytic at all point inside and on a circle of C defined on mod z minus a is equal to r. Here a is a center of a circle, r is the radius. Then for all z inside C, then f of z can be expressed as f of a plus z minus a by 1 factorial into f dash a, that is a first derivative of a, plus z minus a whole square by 2 factorial into second derivative of that function and substituting with the value of a plus etc. is called a Taylor series expansion of f of z. If a is equal to, particularly if you're applying 0, that Taylor series expansion become a Maclaurin's series expansion. That can be expressed as f of z is equal to f of 0 plus z into f dash 0 plus z square by 2 factorial into f double dash 0 plus etc. You know that Laurent series expansion, if f of z is analytic, all the points inside and on the boundary of the annular region are bounded by two concentric circles C1 and C2 with center A and radius is equal to R1 and R2. Then we can express f of z is equal to summation n 0 to infinity an into z minus a to the power of z minus a power n plus summation n 0 to infinity a of minus n into z minus a to the power of minus n. And also here an, where an is a constant, complex constant, that is 1 by 2 pi I into integral upon c1 into f of w divided by f w minus a to the power of n plus 1 into dw, and a of minus n is equal to 1 by 2 pi I into integral upon c2 f of w divided by w minus a to the power of minus n plus 1 into dw. Here we can express this f of z is equal to n from 0 to, instead of in 0 to infinity, we can make minus infinity to infinity an into z minus a to the power of n. Here both positive as well as negative terms of the series. Here if you put this term become 0, this Laurent series expansion reduced to a Taylor series expansion. And also you know that this theorem we already explained in the previous classes. That is, if you two circles will be there, center is here A and C1 and C2 are the we say that it's a concentric circle, means only one center, and radius is equal to R1 and another one is R2. Here we will give some examples related to series. Expand the function f of z is equal to e power z as a power series. First, we can make using Taylor series expansion of f of z is given by f of z is equal to f of a plus z minus a by 1 factorial into f dash a plus z minus a whole square by 2 factorial into f double dash a plus etc. Means f dash a means that is a first derivative, this is second derivative, we already told. And here we, if you take f of z is equal to e power z and a is equal to 0, then we can start this one here. First, the given function is f of z is equal to e power z. The derivative of that is f dash z is equal to e power z. and f of 0 become e power 0 is 1, f dash 0 here also 0 is 1, and also we know that nth derivative of z is equal to e power z is e power z only, the value is continuously it become 1 1 1 up to nth derivative also. And here at least you must make three derivative because we can write it 3 4 terms. That's why if second derivative third derivative become, if you substitute e power z value is equal to 0, then you get 1 1. Then finally you can substitute in the Taylor series expansion. Here f of a and corresponding derivatives, you can substitute, you get 1 plus z square by 2 factorial, z cube by 3 factorial, plus z to the power of 4 by 4 factorial, etc. This is known as the series. This can also be expressed as summation n from 0 to infinity z power n divided by n factorial. If you put n is, this can also be written in a summation notation. These are some important series expansion. You must remember, you already known these things in a real analysis. In place of z, you are express x. Here sin z is equal to z minus z cube divided by 3 factorial plus z to the power 5 by 5 factorial minus z power 7 by 7 factorial plus etc. And cos z is equal to 1 minus z square by 2 factorial plus z to the power 4 by 4 factorial minus z power 6 by 6 factorial plus etc. This also we can make it in a summation notation n from 1 to infinity. Here z minus z to the power of n, then this can be expressed in the series expansion. E power z is a combination of cos z plus I sin z. You can make it into simplification, that is 1 plus z square by 2 factorial plus z cube by 3 factorial plus z to the power of 4 by 4 factorial, etc. And also 1 by 1 minus z is a geometric series expansion, that is 1 plus z square plus z cube plus etc. 1 by z 1 by 1 plus z to the power of minus 1 is here positive and become negative, alternative positive and negative terms will be appearing here, then that can be expressed as 1 minus z plus z square minus z cube plus etc. Suppose if you have minus 2, then you can make it as 1 plus 2z 3z etc. Here also that is minus 2 and 3 4 etc. will if you have a minus 2. Now we will give one more example related to Laurent series of this function. F of z is equal to z to the power of minus 5 divided by, z to the power of minus 5 into sine z, or sine z divided by z to the power of 5. First we can make into a sine z, we already know. We can utilize that series expansion sine z, that is sine z is equal to z minus z cube by 3 factorial plus z to the power 5 by 5 factorial minus z power 7 by 7 factorial plus etc. And we multiply the z to the power of minus 5 for this function, then this becomes z to the power of minus 5 into inside, then this become rearranging, then you get 1 by z to the power of 4 and z to this become 1 by z square. 3 factorial is 3 into 2, that becomes 6 here, then here 1 by 5 factorial. 5 factorial is 1 into 2 into 3 into 4 into 5. If you multiply all, you get 120 minus z to the power of minus 5 plus 7, that become 2 z square divided by 5040. This is the series expansion of this function. One more example related to z square algebraic into exponential function, that is f of z is equal to z square into e power 1 by z. We know that series expansion of e power function e power z can be expressed as e power z is equal to 1 plus z square divided by 2 factorial plus z cube by 3 factorial plus z power 4 by 4 factorial plus etc. Here you can multiply with this function z square on both the sides, then you get Or first you can make e power 1 by z. Then here z is there. In place of z, you can express 1 by z, means in place of z, replacing 1 by z, you get this one. After that, you can multiply z squared to both the sides. You get z square plus z square by z, that becomes z, and z square become cancel. You get 1 by 2 plus 1 by 6z plus 1 by 24 z square, etc. This is the series expansion of the function. Now, one more example related to Laurent series. Here you can expand the function f of z is equal to 1 by z minus 1 into z minus 2 in the region. There are different regions are given. Here the region is given mod z is less than 1, and another one is 1 less than mod z less than 2, and one more region is given mod z is greater than 1, greater than 2. Here, what is the meaning of this is mod z is less than 1 means here the center is equal to 0 and radius is equal to 1, but it is lying inside the points only we can consider. Here, this can be make it into two functions. One is less than mod z and then mod z. 1 by mod z is less than 1. Always you can make it that function mod z is less than a form. Then this become mod z is less than 2 means mod z by 2 is less than 1. And another one is mod z is greater than 2 means that is same as 1 by 2 by mod z is less than 1 form. This is the easiest method to compute this type of problem. First, we can start with applying, first we can make it into rearrangement using partial fractions of this function of f of z 1 by z minus 1 into z minus 2, that is equal to a by z minus 1 plus b by z minus 2, and find a and b values. You get a partial fraction for this. Next, if you rearranging this, that is a into z minus 2 plus b into z minus 1 into is equal to 1. This is one equation. Here, if you substituting z is equal to 2, you get b value. If you substituting z is equal to 1, you get a value. This is the one method. You get a and b value, then it is in the standard form of a Laurent series. Then only we can start. Otherwise, we can make here, if you put, there is a direct method to compute this. If you put here z is equal to 2 in this form here, then this become, what happens, 2 minus 1, that is 1. And here 2 minus 1, a is equal to minus 1. 2. Therefore, this is the value a is equal to minus 1 and b is equal to 1. We can express directly also. Instead of computing this, we can substituting directly, we get the solution. Then after getting this partial fraction, then minus 1 by z minus 1 plus 1 by z minus 2, then different cases we can start. First we can make it into 1 by 1. First, always we can make it into, first case is mod z is less than 1. Here you can see, here z by 2 is always less than 1, and here z is there, exactly mod z is less than 1. Then we can write directly, here 1 by z minus 2 is equal to minus 1 by 2. If you take the 2 outside, then this become 1 minus z by 2. Next, if you substituting this function is directly, we can make 1, because minus sign is here, minus sign. If you take common, that become cancel to each other, then 1 by 1 minus z. Z will be there. You can take it into numerator. It is in the standard form. That is 1 minus z to the power of minus 1, or summation n running from 0 to infinity z power n. Minus 1 by z, this will become 1 minus z by 2 to the power of minus 1. Again, it is also in the geometric series form. Hence, the binomial expansion are expressed using the standard form. This becomes 1 plus z square plus z cube plus z to the power of 4 plus etc. Minus 1 by z, 1 plus, in place of z here, z by 2 plus z square by 4 plus z cube by 8 plus etc. Hence, if you simplifying this, you get this one. Next, again, we can consider the second case, that is case 2 for 1 less than mod z less than 2. Here, I already mentioned this one. One is less than mod z and another one is mod z by 2 and z to the power of minus 1 are less than 1. Then 1 less than mod z, 1 by mod z is less than 1, mod z is by 2 is less than 1. Then we can write directly here, take my z as a common factor, minus 1 by z, 1 minus, this is not there, z to the power of, 1 by z to the power of minus 1 minus 1 by 2 into 1 minus z by 2 to the power of minus 1. We can apply that binomial series expansion, we get minus 1 by z into 1 plus z to the power of minus 1 plus minus z to the power of minus 1 the whole square cube etc. minus 1 by 2 into 1 plus z by 2 plus z square by 4 by z cube by that one. You can substitute, you get a solution for the equation. Then you can simplifying these two, you get this one. Finally, in the last case, for mod z is greater than 2, both here 2 by mod z and z to the power of minus 1 are less than 1. Or then this become minus 1 by z, 1 minus z to the power of minus 1 to the power of minus 1. Here you can take z as a common factor, 1 minus 2 by z to the power of minus 1. Same procedure what we adopted in the previous example, apply binomial expansion, we get here minus 1 by z, it is in the form of 1 minus x to the power of minus 1, apply here 1 plus x, x square plus x cube etc. Substitute in place of x here z to the power of minus 1, you get this one. Similarly here in place of x here 2 by z is there, you can substitute here 1 plus 2 z to the power of minus 1 plus 4 by z 4 into z to the power of minus 2 plus etc. Then we can simplify these two, we get 7 z to the power of minus 4 plus 3 z to the power of minus 3 plus z to the power of minus 2 etc. In this, in the next, we will discuss about the pole and its operation.